Okay, so today I thought we would look a little more detail, or look at a little more detail in the Kepler orbits and classify them according to their eccentricity and see kind of where the bounds are, what are the shapes of the orbits, maybe play around with these conic sections a little bit more. So let's recall that we solved for the radial coordinate in polar coordinates for an object under the influence of an inverse square law force. So an inverse square law central force. And we found that it has a polar form of a conic section. So this P in the numerator, that is the semi-lattice rectum of that particular conic. We'll see a couple pictures of that in a sec. It has a value that depends on the orbital angular momentum of that object. So the larger L is, the greater P is. We also can see these two parameters as a reminder. Mu is the reduced mass of the two-body system, and kappa is usually taken to be G times the product of the masses, but it could also be something else if we're doing something like a Coulomb scattering. But it is the coefficient of your 1 over r term in the potential. We also found that the eccentricity, and I wrote it too many square roots, let's write it as epsilon squared, is also dependent on the total energy and the total angular momentum. And there's a lot of different ways of rewriting these in terms of each other, but this is our general form. And we've chosen our constant of integration, or rather our starting value, to be phi equals 0, and we'll see what that looks like for our various graphs. So now what we want to do is look at all the possibilities we could possibly have. So it turns out that the lowest possible value for the eccentricity is 0. And this is coming from an interplay between two different terms. E and L, if I want to make them both small, I can't do them individually, really. Because E, in a way, depends on L. If you recall what the expression for the total energy of this orbit is, it'll have a radial kinetic energy term, a centripetal kinetic energy or rotational kinetic energy term, and then the actual sort of Coulomb style or 1 over r potential from gravity itself. So if I want to make the energy lower, there's 3 terms to play around with. However, one of those terms has an L squared in it. And making the product of these lower, well, is tricky because we could make E lower, but that usually comes at the cost of having to increase the orbital angular momentum or vice versa. So the lowest possible energy does correspond to this term here exactly equaling -1. And that means that the total eccentricity is 0. Now, what does that mean as far as the specifics to the orbit? Well, if we look at our expression for the orbital equation, this means that r is simply equal to p, which is just L squared over mu k, a constant. Well, what type of orbit in polar coordinates has a constant radius? Of course, that would be a circle. And the picture we would have here is a circular orbit whose radius is just this value L squared over mu kappa. We could have gotten that from long ago mechanics just by thinking about a centripetal acceleration in the usual Newtonian way. Now, this is fine. It does mean that we can go calculate the energy as well, because remember, if I need this whole thing to equal 0, I should be able to write E directly in terms of L and mu and K. This whole thing should be 0. So 2 times E times L squared over mu kappa squared should equal -1. And what that tells me is that the total energy of this circular orbit is going to be negative kappa over 2, well, P, if you want to write it that way. I can rewrite this whole thing as basically a P over kappa, and there'll be a 2 that comes out of it naturally. So that is indeed the energy of this circular orbit. It's negative as desired, and it is actually the lowest energy orbit that is not terribly interesting. There's no radial motion. It is a conic section. It is a, I don't want to say degenerate, but it is a very specialized ellipse that happens to have no eccentricity. Okay, things get a little more interesting when we take epsilon to be some number between 0 and 1. We already covered the epsilon equals 0 case, but what if it's some number between 0 and 1? Well, in this case, we can turn back again to our orbital equation. We recognize that epsilon is some number, again, between 0 and 1. that does mean that my denominator can never equal 0 because cosine itself is also between -1 and 1. And so even if epsilon is getting really close to 1, this cosine being -1 will make this number in the denominator very close to 0, but never actually equal to 0. So the picture we're going to have here is when phi is equal to 0, we know that we're going to have a minimum of radius. Again, this is also called the periapsis. It's the closest approach point to the center of mass of the system. Put an X there. And we can quickly plug in phi equals 0 here and see that that'll be at p over 1 plus epsilon. And then on the other side, we're going to have an R max, which is going to be, well, plugging in phi equals pi gives us a -1, so we'll have p over 1 minus epsilon. And this is called the apoapsis. Then the trajectory itself will just be an ellipse. Not the best at drawing ellipses, so don't sue me, but I think that's decent. Notice that the sum of these two, because this distance is r min and this distance is r max, if I add them together, I should get the entire major axis of the ellipse, which we call twice the semi-major axis. So A would be half of this sum. If I do plug those two values in, find a common denominator, we do actually end up with A equaling p over 1 minus epsilon squared, a result we've seen before. So the semi-major axis of this ellipse depends on p, which really means depends on the orbital angular momentum, and the eccentricity. Again, you can see the eccentricity can start at 0, then we'll just get that A is r, the radius of a circle. As the eccentricity gets really close to 1, though, this ellipse will get very, very large indeed and sort of open up to the left more and more and more and more. We can also go ahead and plug these values in to our original equation here for the eccentricity, if we know what it is, and we'll end up getting the result we've seen earlier, which is that the total energy of this orbit is minus kappa over 2a. So now it depends on the size of the orbit in terms of the semi-major axis. While we're at it, I'll go ahead and label a few of these other things. So here's the center of the ellipse, and we've just said that this distance is a. If I split the ellipse in its other symmetry axis, we have the minor axis and its semi-minor version, which is usually called b. And then if you remember from your high school geometry, there's a relationship between the semi-major axis and the semi-minor axis in terms of the eccentricity. And that's usually defined through a new variable, which I'll call c, which is the square root of a squared minus b squared. This value, I don't know that it really has a name, but it's actually equal to epsilon times a. So if we scale this semi-major axis by a distance or by a factor of epsilon, we'll recover this value c, and that'll be related to both of these semi-major and semi-minor axes themselves. Of course, we could also add in one last thing, which is that this distance is p. That's the semi-lattice rectum. A lot of semis in these. And one last geometrical fact, this c in sort of high school algebra 2 is also sometimes called the eccentricity or the linear eccentricity. And as a distance, let's see if I have any more colors. Green on green, let's see if it works. That distance is actually from the center of the ellipse to either of the foci. There's a second focus over here, so those two distances would be c. So that's sort of the geometrical interpretation of this distance c, and you can see that it is scaled down from a. And as one last thing to mention about ellipses for now, we'll have more to say about them in a future video, we can go rederive Kepler's third law starting from Kepler's second law. Let's recall that the second law says that dA dt, the area that is swept out by our, well, orbital radius as a function of time, is a constant. In fact, that constant we said was the total orbital angular momentum divided by twice the reduced mass. We've worked that out in a previous video. But the case of an ellipse, we actually can solve for some of these things. The total area, since this is supposed to be a constant, I can just write it as the total amount of area that is swept out in the total amount of time that this is swept out. But look, the total amount of time is exactly the period of this orbit. So doing a little cross multiplying, and remembering that we actually do have a formula for the area of an ellipse. Can't do that for the circumference, unfortunately, but the area of the ellipse is actually pi times the two semi-major and semi-minor axes. Okay, so this is looking pretty good. I need to know what B is, and I'd also like to rewrite L over 2 mu. I can see that L over 2 mu is going to be, where was it? Kind of related to P, and then P is related to A in a complicated way. It's not too bad. But let's write out what we know. So this will be 2 mu over L times pi. A I'm going to leave as A. And then B I can get from this relation here. So notice if I square both sides, and then I do a little moving things around and factoring, I can end up with B equaling another A. It'll come out of the square root when I solve for B, times the square root of 1 minus epsilon squared. So that's actually the value for B. Again, square both sides of this, move the B over, subtract that over, factor out the A squared, take the square root, and you'll get that result. And then to finish things off, remember 2 mu over L. I'm going to try to use P here to rewrite that. And what would that be? Let's see, I'll need a 2. So I'll put a 2 pi here. That pi comes to the front. Okay, so to finish that calculation off, I need to know what mu over L is. Let's go back over here and rewrite it in terms of P. If I multiply, or rather divide both sides of this by mu, I'll have an L squared over mu squared. Multiply the kappa over, so kappa times P over mu is that ratio squared. Take the square root and flip it, and I'll have a square root. Like I said, this was kappa P over mu. I'm going to flip it. And then I'll have an A squared and then a root 1 minus epsilon squared. And then in this tiny little space that we have left at the bottom, I want to rewrite P using this relationship, which has an A times a 1 minus epsilon squared. But look, the square root of 1 minus epsilon squared here and this factor will both cancel. And we're left with 2 pi square root of mu over kappa times, well, there's an A square root in the denominator, so I'll put this as A to the 3/2 just to again make this very clear. So again, we can derive Kepler's third law using Kepler's second law and some properties of the geometry of ellipses. Okay, so that kind of looks at the elliptical case. What happens when the eccentricity exactly equals 1? All right, so when the eccentricity is exactly equal to 1, you can kind of see what's going on here. E is 0. It's directly 0. So this would be a total energy of 0, which means it is no longer a bound orbit. It's actually going to escape to infinity. And we can kind of see why that is, because if epsilon equals 1 up here, there is a value of phi that causes the denominator to equal 0, namely pi. So if we look at a graph here in polar coordinates of this particular conic, okay, here's our origin, our center of mass. We're still going to have a periapsis, if that's the right term to use for a parabola. That's when phi equals 0. So that value is still P over 1 plus epsilon. But 1 plus epsilon, of course, is 2 now, because epsilon is exactly 1. And then if we trace out what happens, R will get larger and larger and larger in either direction. We have a parabola. And to label a few other points here, this distance is, of course, P. Notice it's going to be half of the, the total lattice rectum of the parabola passing through the focus. We already just found that this distance here is P over 2. And we see that as phi goes towards pi, this trajectory goes off to infinity. So it does not close anymore like an ellipse does. This actually is an infinite orbit. It makes it to infinity. but it only barely makes it to infinity, meaning because the total energy is 0, as I take the limit as r, this distance goes to infinity, I expect my potential energy to go to 0 also. But if the total energy is 0, that means my kinetic energy also goes to 0 at infinity. So it kind of goes to infinity, but only arrives there with no total kinetic energy. Okay, so that one's actually not terribly interesting. It's a knife's edge balance between just barely being an unbound orbit. Not much more to say about that. Now let's turn to the very unbound orbit, which is epsilon greater than 1. So this one was a parabola. And now we're going to look at hyperbolas. So when epsilon's greater than 1, we definitely can divide by 0 here, and not just at one value of phi, when phi is pi radians. We're going to end up with, well, an angle at which we have asymptotes, not just sort of a going to infinity very, very slowly, but rather approaching an asymptote. Okay, so that means my energy is actually greater than 0. It means that even at infinity, there will still be a v. Let's call it v infinity, I guess. And you can just go back to the original definition of the energy of these orbits, and it's going to be root 2e over mu. Okay, so that is the sort of speed at infinity. The graph is our typical graph we might see, again, imagining something from high school. We're still going to have this periapsis, and it's still given by plugging in phi equals 0, so it's still p over 1 plus epsilon. Epsilon's now greater than 1. And then we're expecting something that goes off to infinity rather quickly along these asymptotes. Doing the best I can with these drawings. Okay, so this particular angle that we see this making is going to be some asymptotic angle. And you can figure out what that angle is, right? That angle is going to be, say, arc cosine of minus 1 over epsilon, just by setting this denominator equal to 0. We could drop the negative sign because the arc cosine function is even, at least over the range we're looking at here. Now we'll examine the geometry of hyperbolas more later, but one thing we want to recognize is there is another b that shows up pretty naturally here, and that's this distance. This value b is sometimes called the impact parameter. It's the point of closest approach of this asymptotic dashed blue line trajectory. So it's kind of the closest the particle would get to whatever the center of mass is if it was shot in along a particular direction. Now, of course, it gets closer than that because there is attractive gravitational force that deflects it, but that value b we're going to see shows up in a couple other ways in the general geometry of hyperbolas. You might also notice this is only one branch of a hyperbola. A true hyperbola should have 2 branches. So what happened to the other one that's sort of over here? Turns out that that branch of the hyperbola is going to be useful when we're looking at scattering from a positive, repulsing potential energy. For example, if I was looking at the scattering of a charged object versus a similarly charged object, meaning like both positive or both negative. The other branch of the hyperbola would help us understand what the trajectory of that particular object would be. So the other branch does make an appearance if kappa in all of these formulas is sort of negative in a sense, but we'll leave that for a different discussion. Okay, so I think that's a pretty good classification of these orbits. They can all be classified totally by their eccentricity. 0 eccentricity is a circle. Between 0 and 1 is an ellipse. Exactly equal to 1 is this parabola, which is unbound. It's infinite in extent. And then greater than 1 gives us our family of hyperbolas. And these hyperbolas, again, have a total energy greater than 0, which means this object, this mass, etc., goes off to infinity and kind of it makes it to infinity with leftover energy. Notice that it still has speed even at infinite distance. So it's sort of very unbound in a sense. All right, I think that's pretty good classification. We'll look at some more properties later on. QED.